sleep-deprived brain is mush. So confounding, anything other than the explanatory that affects our response. So here we saw sun exposure. Are there other things that I didn't consider that might affect plant growth? So sun versus shade, what else? Soil conditions. Yeah, amount of water they were getting, the nutrients that are in each half of the field, were they the same or different? Were those plots identical or not? These are all things that we have to consider as researchers as we're planning our study. Because what we want is to isolate the effect of the explanatory on the response. And all those confounding variables are going to make that more difficult. So in order to accurately determine the relationship between the variables we are interested in, we need to control for any potential confounding variables. And before we get into the formal stuff, we're going to go back to our example of my field, fertilizers A and B. What could I do to my setup that would control for that sun exposure? So take about 90 seconds in your small group and discuss, how could we set up my field so that I can control for the sun exposure versus shade? You can't change the sun, but what can you do to set up the field that will mitigate the effect of it? Sorry, Prasanna. Ooh, yeah. Another group came up with that same idea. Good. Wait, what? No. I mean, if that helped you make sense of it, you could. All right, Bailey, my FFA person who is super excited to share. What do you want to share? Cut it landscape. Can I get a thumbs up? Who else had that idea? Yeah, I saw that at a couple of tables. Very good. Doing it this way, here's my A, here's my B. Make sure that both A and B are getting some of it in the sun and some of it in the shade. So now I know A versus B when it's sunny. I know A versus B when it's shady. I've mitigated the effects of the sun because both fertilizers are getting the same sun exposure. Very good. Very good. That idea that if I have variables that are popping up, I want everybody to get the same treatment. That's the idea of control. So in statistics, control means that I am keeping all of the other variables in the study other than the explanatory the same for all of the treatment groups. Whoops, I keep forgetting the pen. I want the same conditions across all treatment groups. VARs, variables. Sort of like the VARs button on your calculator stands for variables. Yeah, VARs. Sorry, my writing is big and I'm tired and yeah, VARs. So control means all of my treatment groups. In the field example, old fertilizer and new fertilizer are experiencing the same conditions, except for the variable of interest, the fertilizer. So both cases, they got half sun, half shade. Good. All right, new example. Team at UC Davis developing a medication to treat the pain that results from arthritis. They have developed a new 50 milligram pill. They want to test it. And they're going to test it versus a sugar pill that has no active ingredient. Looks the same as the new medication, but there's no actual medication in the pill. So let's start with what is the explanatory variable and what is the response variable. So remember, explanatory is what the researcher is controlling or manipulating. The medication, very good. And what is the response variable? What is this medication hoping to treat? Arthritis pain, yeah. Come on, pen. So that was 3A, right? We're familiar identifying explanatory and response. We are going to see some new vocab. For each explanatory variable in your study, we call that a factor. So factors are explanatory variables. This study has one factor, the medication. Levels are the categories within that explanatory variable. So for our medication, what are the types of treatments that I'm giving to my patients? A pill, but there's two types of pills. Very good. The 50 milligram that has the active medication. The sugar pill, which has no milligrams of the medication. Yeah. Those are levels of the same factor. And we're going to compare the levels for that factor. So factor is the variable, levels are all of the little subgroups of that variable. Yeah. You're going to see that vocab on the AP test. Yeah. I see you turning the page. Very good. Tied to this medication example, there is, this unit is nothing but vocab because there's no math in it, right? Yeah. Note cards. That's why I told you at the beginning, you should be making note cards as you go, right? Vocab alert. The placebo effect. Who's taken psychology here or is in psychology currently? Not as many as I thought, but about a quarter to a third. Yeah. Placebo effect is a psychological effect that happens when the subject responds to a treatment that does not contain any active ingredient. In our example, this would be somebody in our study saying that they experienced a decrease in their arthritis pain even though we gave them the sugar pill. Yes?
Is it like the same thing as when like people like cancer patients, like when they like I don't know, eat mercury or something, like would that be a placebo effect? Because it's not something that's actually helping them.
It's not helping them, but their brain thinks it is, and so their body responds. Yes, that is the same effect. Good. This is purely psychological. This is the power of the human brain and the brain's effect on the body, right? You think you're getting treatment, and so your body responds to what it thinks it's getting, even though there's actually no active ingredient. And the question that I'd like you to consider in your small groups is, as that UC Davis researcher team, how can I combat that psychological effect? I'm going to give you about 90 seconds in your small group. Those of you who've taken psych may have a clue. How can we combat that effect? How do I prevent the placebo effect from affecting the results of my study?
You are like.
Hello. I'm good, thanks. How are you? I'm glad. Fine is okay. Take fine. Yes, Marissa?
We're having an argument right now.
You're having about?
Okay. So, does that mean that you don't tell them? Would it be you don't tell them
Because you don't want it
because you don't want it to affect it? Or would you tell them because it's going to have that effect if you don't tell them?
No, you don't tell
Like,
them.
you get what we're saying?
You psyched out Bailey with a smile at her.
All right. I need us to come back together. And I need some ideas. So, Isabel G., what ideas did your table discuss? Does that mean we're not sure? Okay. Yes, Bailey. Did anybody else come up with a different idea? Good. Anything else? No, both of those are good. Notice both of them involve withholding information. And the idea that we are withholding information in a study like this is called blinding. And there are two types of blinding. There is a single blind study and there is a double blind study. So, we'll start with single blind, which I think is what you guys were suggesting. Don't tell the participants what's going on. Yeah? So this could be withholding information from participants. I think I spelled that right. I think there's a double H. I have no idea. I'm going to go with it. There's a reason I majored in math. There is another option here. Single blind, I can withhold information from the subject. Or from, I'm going to say researchers here. Researchers isn't exactly the word I'm looking for. Really what I want to do, I want to withhold information on the research side of it is I want the people that are interacting with the subjects to be blinded. Because chances are, as the researcher, I'm not the doctor who's administering the meds to the patient in a doctor's office, right? So I want the doctor who's interacting with the patient to not know which pill they're giving the patient. So I want the people interacting with the subjects to be blind, or I want the subjects themselves to be blind. That's single blind, one or the other. Double blind is when neither of them knows. That's really common because that prevents bias from the researcher end as well as mitigating the placebo effect on the subject end. Because as the research team, including the people interacting with the subjects, if I don't know who's getting what, I can't see something that's not there, right? If I created this med, I'm really rooting for it to work. I can't see effects that aren't there if I don't know who got what. So this is really common because it eliminates bias on both sides. Very good. Questions so far? It's a lot of vocab, I know. We good? Yes? We're awake because I can hear you talking. That's a good sign. All right. So I believe it was Ostap who asked this question. It was a very thoughtful question, but he asked it way too early. And now we're ready to answer it. What makes a well-designed experiment? And there are 4 things. The first is that I need to be doing some type of comparison. What did I write earlier? Oh, there we go. So we're going to use 2 or more treatments, or we're going to do treatment versus control. The control group is the group that has everything the same, but they're not getting the treatment at all, right? This would be the sugar pill group in our case. So I need a basis for comparison. Otherwise, why am I doing an experiment? Second, random assignment. Subjects should be randomly assigned to treatment groups. We have a clue of what this looks like. We already know how to do random sampling. We know how random number generators work using that same principle here. If I have 200 subjects, I'm going to randomly select 100 and stick them in research group 1, and then the remaining 100 are in treatment group 2. The next is replication. And you may be thinking, if you've taken other science classes, that means my experiment gets repeated in multiple places. That is repeatability. That is a different idea. This means my sample size is large enough that when I see an effect in the response, I know that it is not just chance variation in the sample, which is a big idea. I want to make sure that my sample size is large enough that each of my treatment groups has enough people in it that those samples are going to be approximately the same in terms of composition of people. Never perfectly identical, right? But if I'm sorting into treatment groups of adults, I want to make sure that each of those groups has about the same number of men and women, about the same number of people in each age group. I want to make sure it's evenly distributed. And in order to do that, I need a big sample, right? If I only have 10 people in my study, it's hard to make sure that those two groups look the same. So big samples. The last is the idea of control. We need to control all of the potential confounding variables. In our field study, that meant planning our fields in, I believe you said landscape mode, so that fertilizer A was sun and shade, fertilizer B was sun and shade. If I'm doing that med experiment, it's making sure that those groups have an equal distribution of age and gender and all of that other stuff that might affect the response to the medication. Okay. So there are 3 types of experiment designs that follow that principle that we are going to talk about, that you will be asked about on the AP exam. Most years there is at least one question on the FRQ that comes from this. So we're going to go through them in detail so you know what they look like. Yeah. Shoot, fly. All right, first one is completely randomized design. Completely randomized design in terms of experimental design is the equivalent of simple random sampling when I'm sampling from a population. This is the gold standard. It is the basis for all the others that we're going to do. And the only principle here is that we are using random assignment to treatment groups. Bless you. It is that time of year. So first we're going to draw a picture of what that looks like, and then we're going to do some writing, because the AP board on the FRQs is going to expect both diagram and explanation. We'll start with the diagram because the visual is usually how we process things in our brain. So I'm doing my medication experiment for the arthritis medication. I start with 1,000 sample subjects. And I want to sort them into treatment groups. Which 2 treatment groups do we have? 50 milligrams and sugar pill. Very good. So 50 milligram pill and 0 milligram pill. So I want to split them this way. And to do that, I am going to use random assignment. What the AP board expects to see is that in your picture, you've labeled random assignment. And then below the picture, you have described what your random assignment process looks like, which we'll do second. Yeah? I'm going to split up 1,000 people into 2 groups. How many people should end up in each group? 500. I'm going to split them in half. Yeah. So this should be 500 subjects. This should be 500 subjects. If you have an odd number of people, one group will have one more than the other. That's not a huge deal. Please don't try and cut people in half and put 0.5, 0.5. That's bad. Very good. And after this, the feature of a good study is then I bring these back and I compare the results. That was the first property of a good study, is I'm going to do comparison at the end. Compare the treatment groups to each other. Simple picture? Yeah? Conceptually not difficult. Here comes everybody's least favorite part of this process, which is I now have to explain in detail how I am doing the random assignment. You cannot, you must write it out in words. Otherwise you lose points, lots of them. Please do the writing. All right, so random assignment works similar to random sampling. What is the first thing that I do when I'm doing a random sample? Starts with an L. Label. Yeah, so I'm going to label, come on, pen, subjects from 1 to 1,000, because I have 1,000 of them. Assign each of them a number. Yes, you have to write that out in words. Assume the person reading your paper is stupid. After I assign them a label, what do I do next? It's the R step. It's the randomize step. Very good. So we are going to use a random number generator. To select, and how many people do I want in my first treatment group? 500. So I'm going to select 500 random numbers from 1 to 1,000. Do I want repeats as I'm drawing numbers? No, because I want 500 unique individuals in that first group. So I'm drawing without repeats. So this is without replacement. What am I going to do with those 500 people that I selected? Where do I put them? In a group. Which group? So I have to pick one. The 50. Let's put them in the 50. Good. So we are going to assign these subjects to, does it matter that I chose the 50 milligram group here? No. Good. I just need to assign them to a group and I need to be specific. Doesn't matter which one, but be specific. So we assigned the first 500 people selected without repeats to the 50 milligram group. What do I do with the rest of the subjects? 0 group. Good. 3. Remaining subjects are assigned to the 0 milligram group. Yes, Marilyn. That is a really good question. So for the first 5 questions, they are unit specific, meaning you'll be a question just from unit 3, and you get 13 minutes. For the last question, question 6, it is an exploratory task that's going to span multiple units. That one you get 25 minutes for. It is important to note that they are just going to give you 90 minutes for the FRQ. There is no timer that is going to pop up and say you should be moving on to question 6. So you need to know about 13 minutes per question so you have enough time to answer question 6. Do not do question 6 first. Students who have done that in the past never got to questions 1 through 5. So 1 through 5 first. Yes, I know this is a lot of writing. Yes, I know this is tedious. If you practice it on your homework, it will be less painful. I will do it. It'll be less painful when you have to do it on test day. So please, on your homework, practice the writing. I have a burning passion for this group or this program. I know that there is a student by that name because she's in my class. I guess she's just not getting any help pass today. Okay. Come back together. We've got 2 more questions on completely randomized. No. Okay. For the next 2, I am going to skip this step just because it looks the same for all of the things we're doing. There is an expectation when you are doing this on your homework, you are doing the writing for every time you are doing an experiment design. I didn't assign lots of them, yeah, but you need that writing practice. All right, next one. Hold up. What were you doing while I was dealing with bathroom passes? Anything? No, thank you, Amanda. I appreciate that synergism. That's very good. All right, next one is randomized block design. This is going to sound very familiar because it looks like stratified sampling. Raise your hand if you can describe to us what stratified sampling looks like. Amanda. Very good. We sort the population into groups. We take a random sample from every group. Similar idea. We're going to start randomized block design the same way we start stratified sampling. We are going to divide our subjects into group based on some characteristic. By age group, by gender, by income level, by zip code. Pick a characteristic that you like. You can take pictures with your cell phone if that helps. And then write it. Yes. Oh, you can go. When it's time, you can go. Yeah. You've got like 5 minutes. Once I have divided them into groups based on this characteristic of interest, age, gender, income level, I then split each of those groups into treatment groups using random assignment. So within each group, use random assignment to split them into treatment groups. That is not how you spell split, Mr. Jolliffe. Meaning we are splitting twice. First by some characteristic. That's not random, that's specific, that's based on our interest. Once they're split into groups, I'm then going to go into each group and split them using random assignment into treatment groups. So while you are jotting down the last of that sentence, think in your head, if I am doing my arthritis medication study, my arthritis medication experiment, what kind of characteristic might I want to subdivide my subjects into? So I'll give you a second to cook for a second. That didn't come out right, but you know what I mean. All right, Marilyn, what are you thinking? How do we want to split them up? Yeah, you. By age, that makes sense, because arthritis affects people in different age groups. Very good. So we could do this by age. What kind of dividers would you like by age? Like, yeah, like give us some ranges here. I want to take my 1,000 subjects. I want to sort them by age. 30 to 40 years old. And then I heard 40 to 50 years old. Come on, pen. And then I'd guess 50 to, my instinct is 50 to 60, and then over 60. Does that work? Notice that when I take my 1,000 subjects and I split them by age range, it's very unlikely I'm going to get equal age ranges. It's unlikely that there's 250 in each of those 4 groups. So let's say lots of old people, 600, 200. Probably wouldn't be that neat and pretty in reality, but I'm trying to come up with numbers off the top of my head. So there we go. That adds to 1,000. So that's the first step. I have sorted them by age range so I can compare across age ranges. Now what do I do? Split the treatments. Very good. So within each group, random assignment to treatment groups. Perfect. So here I'm using random assignment to either the 50 milligrams or the 0 milligrams. I have to do the same thing for the 40s to 50s. Random assignment to 50 milligrams or 0 milligrams. All the way down the list. Random assignment to treatment groups. Yes.
So this one has like nothing to do with the previous one?
So this one is, you'll notice within each of those categories, this looks like completely randomized design. So within each of those subgroups, I'm doing completely randomized design. But now I'm doing completely randomized design on subgroups of interest. Sort of like with stratified sampling, I split it into groups, and then I use simple random sampling on each group. Similar idea. When I look at how many are in each of those treatment groups for the 30 to 40 age range, how many people in each of those treatment groups? 100. Good. That split by random assignment should produce approximately equal groups. So 100 people here, 100 people here. 40 to 50, I had 200 subjects. I should split them equally between the med and the sugar pill. 40 to 50, I had 200. I should split them equally between the med and the sugar pill. For the 60 and over, or the over 60, how many people in each subgroup? 200. 400 people, half of them to the 50 milligrams, and 200 to the 0 milligrams. Words are hard. Once we have collected the results for each of those branches, we go back and compare within the subgroups. And again, that looks like a completely randomized design by subgroup. I've done 4 separate completely randomized designs. So stratified sampling is very similar to randomized block design. We're doing completely randomized design by subgroup. Yes, Isabel? So typically the AP test is going to ask you about one type of experiment and ask you to describe it. So one picture, one explanation of how you randomized it. No, they're not going to ask you to do all 3. That would be mean and take too much time. All right, questions on randomized block before we do the last one? No, last one is called matched pairs design. Matched pairs design has 2 different variations. We're going to start with the most common, and then we'll look at the less common. Yeah. For matched pairs design, all of the subjects get both treatments. And what should be percolating in your brain is, how do we make this random? Because I know to be a well-designed experiment, I have to use a random assignment somewhere. And if they're all getting both treatments, how do I do random assignment? And the answer is the random assignment determines the order that they take the treatments in. So random assignment determines order of treatment. Meaning about half of my subjects will get the sugar pill first, the other half will get the Actimed first. So, picture-wise, deep breath. 1,000 subjects. And I'm splitting them into 2 groups. The first half are going to get 1 pill first, and then the other pill. The second group is going to get them in the reverse order. And with medications like this, there would probably be a waiting period in between the first treatment and the second, so that both groups had time to let the first medication clear their system before they took the second pill. And we decide which of those 2 rows they fall in using random assignment. Label them from 1 to 1,000, use a number generator to choose 500 numbers at random, slap them in the first group, leftovers go in the second group. Well, and then we do the comparison at the end. Yeah. That's it, just that first random assignment. Split them in half. Typically, the randomized block design will be the most complicated. The other 2 are pretty straightforward. So 500 people here, 500 people here. Nice, pretty, simple. The alternate design to this is a lot less common because it typically happens when we have twins. Otherwise, it is very difficult to get two people who are identical. The other option is that you have two identical people. One gets one treatment, one gets the other. And random assignment determines who gets what within each pair. So we're running parallel experiments on identical humans. That's very uncommon. This is way more common because this doesn't require us to have two identical humans. It's the same human getting both. Yeah. When you look at twin studies, they often fall in this category where we're doing two different treatments, one to one twin, one to the other. Okay, questions on matched pairs design? No. All right, you're almost done. One more thing, really quick. Deep breath. You're okay. Look how short that is. That's teeny. Almost done. All right, the last part is important, because the whole point of the experiment is to draw conclusions, also known as making inferences. And how we built our experiment determines what kind of conclusions I am allowed to draw statistically. So, if I use random sampling, that's how I chose the subjects to begin with, that means that my sample is likely representative of the population as a whole. That's why we use random sampling. So if I use random sampling, I am allowed to make inferences about the population I pulled the sample from. If I see a relationship between use of the 50 milligram pill and a decrease in pain for the sample, if I use random sampling, I can then make a statement that I expect to see a relationship between use of the medication and a decrease in pain in the general population. The other type of inference only applies to experiments. If I have random assignment, meaning I used a random chance method to assign people to treatment groups, I am allowed to make inference about cause and effect. Meaning if I randomly assigned my people to the sugar pill or 50 milligram treatment groups, and I saw a decrease in pain med for the 50 milligram pill, I can then state that the 50 milligram pill caused the decrease in pain. So random sampling allows me to generalize my results to the whole population. Random assignment allows me to make statements about treatment causing result. Ideally, we're doing an experiment, we have both. We would randomly select the subjects for our sample, and then we would use random assignment to split them into treatment groups. In medical experiments, sometimes that first one is difficult. So oftentimes, when it involves medical treatments or medical procedures, we only have the second one. Meaning we know that A causes B, we're not 100% sure that it's going to work for everyone in the population. All right, so this is the end of our discussion about setting up statistical studies. Our next unit is going to be on probability, which is how we are going to go from making statements about samples to making inferences about the population. And when I see you in semester 2, nothing but inference about the population and all of the ways that we can run those tests. No, that's the fun stuff. That's the power in stats. It's not easy or hard. It's kind of moderate. Like, it's not going to be a walk in the park, but you guys can do it. It is repetitive. So once you get it, it is the same thing over and over and over again with different numbers. All right. We have lots of time before lunch. Please use that to work on your homework. You will notice that 3C, a little bit longer than 3B. I want you to process what we just talked about. Use class time wisely. If you have questions, let me know. Give me 1 second. Yes, Marissa.
This might be a dumb question.
No question is a dumb question.
I started the 3C homework and I got stuck on the 5 levels. So would you say, there's 2 factor levels and then name them, or would you just be like,
There's one
50
factor.
and then 0?
There's one factor, which is our medication. There are 2 levels of that medication. I'm either giving them 50 milligrams of it or no milligrams of it.
So you would say the factor levels are 50
And 0. Yep.
Okay. Thank you.
Yep.
That was a question.
Think of it like factor is the label, and then levels are the actual treatments. A second. Okay, you guys got all your stuff back. Yay. That's a big ask. Pay for your college.
I know. I look good in that picture.
You heard her, Isabel. Get back to your seat. Oops.